Welcome to Curiosity, the podcast where science meets wonder. Join us as we explore the fascinating, the innovative, and the unexpected, from the secrets of the cosmos to the marvels of everyday life. Each episode takes you on a journey to uncover the knowledge and stories that fuel our endless quest for understanding. Let your curiosity guide you.
We are a species that is, I think it's fair to say, obsessed with looking up.
Absolutely, to the stars.
We launch these incredibly sophisticated probes to Pluto. We have rovers crawling across the face of Mars, and we track the cosmos down to, a single photon.
Our technological ambition is almost entirely directed outward, away from home.
But I want you to just stop for a second and consider the ground directly beneath your feet. Right now, if I were to ask you, how much do we actually know about the kilometers of rock beneath us?
The answer is profoundly, and I mean profoundly, humbling.
It is, isn't it?
It is, truly. We often hear that old cliche that we know more about the surface of the moon than we do about the deep ocean floor.
Right.
We should probably add that we know more about distant galaxies than we do about the lower layers of the very crust we live on.
Exactly. And that is why we are going to take a really close look today at a scientific project that stands as one of humanity's most profound, most challenging physical achievements, even though it's relatively obscure.
We're talking about the Kola Superdeep Borehole.
Known scientifically as SG3.
This is a tiny, incredibly narrow shaft that plunges deeper into the Earth's crust than anything else ever engineered by humans.
And it's located in, about as remote a place as you can imagine.
The remote, frozen tundra of the Kola Peninsula. It's deep within Arctic Russia, near the border with Finland and Norway. It's essentially a vertical tunnel straight into geologic deep time.
And this is the crucial part for me. This massive undertaking, it wasn't drilled for resources.
Oh, not at all.
There was no oil, no gas, no gold to be found. This is a purely scientific endeavor.
A massive 2-decade-long state mission to retrieve ancient rock samples and test fundamental geological theories. Theories that, until then, were developed only using indirect methods.
It was a mission for pure knowledge.
Pure knowledge, yes, but also funded by national pride. You can't really grasp the significance of Kola without seeing it as a direct counterpoint to the American Apollo missions.
A sort of geological space race.
Precisely. While the U.S. was focused on the space race, that outward push to the moon and stars, the Soviets conceived of this project as their own demonstration of technological and scientific superiority. They called it the race to the Earth's core.
The scale of this achievement is it's difficult to contextualize. The final record depth reached was 12,262 meters.
Which is 7.5 miles, or over 40,230 feet, straight down.
To put it simply, no human has ever physically traveled a vertical distance like that through solid rock.
And yet, if you went there today, the entire site is sealed with a modest metal cap.
You could walk right past it.
You could walk right past it and have no idea you were standing on the deepest man-made intrusion into the planet. A true engineering marvel, precisely because it required this sustained, delicate effort over such a long period.
But before we get into the engineering, we have to talk about the location. Why Kola? Why that specific spot in the Arctic tundra?
That's a critical point. They didn't just pick a random spot on the map.
They chose the Kola Peninsula because beneath that harsh frozen surface lies the Baltic Shield.
And the Baltic Shield is one of the most stable and ancient blocks of continental crust on the entire planet. It's composed of Precambrian rock. I mean, we are talking about geology dating back nearly 3 billion years.
3 billion.
These rocks are incredibly dense, highly metamorphosed, but they hold the earliest, most pristine records of the planet's history.
So if your mission is to study the planet's beginnings,
Right.
to understand how the continents formed, how life began, you couldn't take a better, older canvas to drill into.
You're guaranteed to be drilling into the deepest history accessible to us. The decision to drill there signaled that this wasn't just about breaking a depth record, it was about scientific sampling.
They were looking for secrets written in rock that predates complex life itself.
Absolutely.
Okay, so let's unpack this. The commitment to knowledge was clear, but the execution was, an engineering marathon of epic proportions. How exactly did the Soviets manage this incredible feat, and what were the staggering physical hurdles they had to overcome just to create a tiny hole in the ground?
The project officially began on May 24th, 1970.
Using a rig called the Uralmash 4E.
That's the one. And when you think about the 20-year timeline, you have to frame it as a marathon, not a sprint. This was because of the incredible precision and patience required for scientific drilling.
Which is fundamentally different from commercial drilling.
Completely different. The contrast is key. When you drill for oil or gas, you're usually aiming for a known reservoir, and speed is everything for commercial return.
Time is money.
Exactly. At Kola, the core sample itself was the primary commodity. The rock was the treasure.
So every few meters, they had to stop what they were doing.
Every few meters. They had to pause the drilling, extract a meter-long cylinder of rock, the core, and then lift the entire drill string.
Which is a distance of several kilometers.
Several kilometers of pipe, yes. They'd lift it all out, catalog the sample meticulously, and then relower the entire string to continue drilling for another few meters. It made the operation incredibly slow and unbelievably complex.
That constant need for core sampling, stopping the rotation and retrieving kilometers of pipe, must have dramatically slowed them down.
Oh, it did. It's why it took 2 decades.
Can you give us some insight into the technology they used? I've heard the Soviets often had specialized methods for this kind of deep drilling.
They did. While many Western companies at the time relied primarily on rotary drilling, which means turning the whole drill string from the surface.
Like a massive miles-long screwdriver.
A good analogy. The Kola project, however, often utilized something called turbo drilling. This is a distinct Soviet technology.
How does that work?
Instead of mechanical torque from the surface, the drill bit itself is spun by a small turbine located right above it. That turbine is powered by the circulating drilling fluid, or mud, being pumped down the pipe.
That sounds much more efficient.
Yeah.
It must reduce the stress on the pipe over those vast distances.
Precisely. For a whole 12 kilometers deep, trying to rotate the entire drill string from the surface introduces massive friction, wear, and torsion stress. The pipe twists.
It could snap.
It could and did. Turbo drilling allowed them to concentrate all that rotational energy right at the bit face. It improved stability and dramatically reduced the chance of pipe failure. It was one of the key technical innovations that allowed them to reach their initial record.
And they achieved an early success with this method, showing the whole concept was feasible. By 1979, they'd reached 9,584 meters.
And in doing so, they surpassed the previous drilling record, which was held by the Americans.
That must have been a huge morale boost in the context of the Cold War rivalry.
A massive win. But reaching 6 miles down was just the prelude. The subsequent 2 miles, from 10 kilometers down to 12 kilometers, presented exponentially more difficult challenges.
Because now you're drilling a hole roughly the width of a dinner plate.
About 9 inches.
You're keeping it perfectly straight, 7.5 miles down, through ancient rock that is getting increasingly hard, increasingly hot, and just plain unpredictable.
Let's use that scale analogy again because it really helps you, the listener, get a handle on this. We know the deepest part of the ocean, the Challenger Deep in the Mariana Trench, is about 7 miles deep.
Right, but that's through water.
Exactly. Kola went deeper than that, but through solid, highly pressurized rock. It's a fundamentally different and much harder physical challenge.
The rock itself was granite and gneiss, right?
Yeah.
Billions of years old.
Immensely dense stuff. And consider this. The Kola borehole is 15 times deeper than the deepest gold mines in operation today.
15 times.
And that visual aid we often use. If you were somehow able to drop the Burj Khalifa, the world's tallest building, into the Kola borehole, it would fall for nearly 5 times its own height before it even hit the bottom.
That vertical commitment is just staggering. But the complexity of maintaining that precision over 2 decades, it inevitably led to disaster, didn't it? Especially as they got close to their goal.
It did. They experienced what every deep driller dreads. In 1983, or it might have been early 1984, the exact timeline is a little blurred in the records.
As they were nearing that 12,000 meter mark.
The combination of extreme heat, the immense pressure, and just the sheer weight of the drill assembly caused a catastrophic failure. The entire drill string snapped.
And we're not talking about a small tool here. We're talking about, what, kilometers of pipe?
5 kilometers of specialized, expensive drilling pipes and equipment. It all just sheared off and fell to the bottom of the hole.
5 kilometers of steel and carbide. Just
Lost. The recovery effort was monumental. They tried fishing for the lost equipment, but at that depth, with the high temperatures and the narrow bore, it was essentially impossible.
So after 13 years of effort, abandoning the whole project was a real possibility.
It was on the table.
So what was the solution that allowed them to continue this marathon?
They performed an extremely precise, almost surgical technical maneuver. They sealed off the failed main branch at a shallower depth, around the 7,000 meter mark. And then they began drilling a completely new parallel shaft that branched off the original hole.
So they had to drill a controlled curve, 7 kilometers underground.
An incredibly precise operation. It really demonstrated the Soviet leadership's unwavering commitment to the scientific goal. They were not giving up.
They didn't abandon the dream. They just found a new path down. And that persistence paid off.
It did. By 1989, they managed to push this new branch to its ultimate final depth, 12,262 meters. But as you noted earlier, that was the end of the line.
The whole stop.
Not because they ran out of pipe or passion, but because they hit the fundamental physical limits of deep crust geology. The heat and the way the rock was behaving were simply insurmountable with the technology they had in the 1980s.
And while the engineers were ultimately defeated by physics, the scientists had already gathered enough data to completely challenge our fundamental geological understanding.
Oh, absolutely.
This is where it gets really interesting, because what they found down there didn't just confirm theories. It fundamentally contradicted decades of geological assumption.
The direct physical samples provided what scientists call ground truth. For the first time, geologists were looking at the actual material that remote sensing-like seismic surveys had only guessed at.
And the first, most shocking revelation was the complete absence of a major boundary they were absolutely certain they would find.
The Conrad discontinuity.
Explain what that boundary was supposed to be and why it was so central to our understanding of the Earth's crust.
Well, for decades, geologists believed that the continental crust was structured in two distinct layers. You had an upper, lighter granitic layer.
The stuff continents are mostly made of.
Right. And below that, a lower, denser basaltic layer. The Conrad discontinuity was supposed to be the sharp, dramatic change in rock composition marking that boundary.
And they knew it was there because seismic waves bounced off of it.
They bounced off it very strongly. So all the models predicted they would encounter this discontinuity somewhere around 5 to 7 kilometers down.
So if the model held true, at 5 kilometers, their drill should have abruptly transitioned from granite, which is rich in silica and aluminum, to basalt, which is much denser and richer in magnesium and iron. A completely different rock type.
Exactly, that was a prediction. But what did the Kola core samples actually show when they drilled past 5 kilometers, then past 7 kilometers, and through the very layer that was causing that seismic reflection?
The rock remained granitic.
It just kept coming up granite and highly metamorphosed gneiss. The dramatic compositional shift, that clear boundary, it simply was not there.
Which must have sent shockwaves through the geology community.
It forced a fundamental reevaluation of everything. It meant that those strong, clear seismic signals that had underpinned structural geology for decades were likely not caused by a change in rock composition.
So it wasn't a change from granite to basalt. What on earth was causing the seismic waves to bounce back so strongly?
The key implication was that the reflections were being caused by changes in the rock's structure. Specifically, metamorphic processes driven by intense heat and pressure, and crucially, the presence of fluid-filled fractures.
Wait, fluid. Water.
Water, steam, other gases. As rock heats up and compresses, its internal structure changes. It develops microcracks and layering that reflect sound waves beautifully, mimicking what looks like a change in rock type from the surface.
So a core assumption about the planet's internal structure was proven wrong by this one drill hole.
It's astounding. Our entire model of the upper crust was based on misinterpreting the echoes bouncing off pressurized steam and cracks in the rock.
It really speaks to the necessity of direct sampling, of getting your hands on the actual material.
It does. And speaking of pressurized fluid, that leads us directly to the second massive, completely unexpected finding, the presence of ancient deep water.
Right, because the conventional wisdom was that due to the immense temperature and pressure at depths, around 7 kilometers, any groundwater would have been sealed off by impermeable rock or just boiled away.
That was the logical assumption. Yet, at about 7 kilometers down, they found large sections of fractured rock that were completely saturated with water.
And this wasn't just surface water that had seeped down over millions of years.
Not at all. Isotopic analysis proved this water was ancient, potentially billions of years old. It was completely isolated from the surface hydrological cycle.
So how did the water get there? If it didn't come from the top, it must have come from the rock itself.
You're hitting on the mechanism. It's a geological process. Under the incredible lithostatic pressure, the crushing weight of 7 kilometers of rock above it,
Right.
The water molecules, the oxygen and hydrogen atoms that were chemically bound within the crystal structures of the silicate minerals, they were literally squeezed out of the rock. It's a process of metamorphic expulsion.
So the rock was literally bleeding water under duress.
Essentially, yes. And the pressure of the surrounding rock was so immense that it kept this liberated water in a liquid state, preventing it from boiling, even though the temperature was far, far above 100 degrees Celsius.
Which completely changed the understanding of Earth's water cycle.
It suggested that vast ancient reservoirs of pressurized water exist permanently locked within the deep continental crust, which was a revolutionary idea.
These are major revisions to structural, geology, and hydrology. But the third discovery takes us into an entirely different realm, challenging our ideas of where life itself can exist: the deep biosphere.
This is perhaps the most captivating finding for the general public, and for good reason. At nearly 4 miles down, in rock dated back over 2 billion years,
2 billion.
scientists discovered microscopic fossils. We're talking about the preserved carbon and nitrogen remnants of 24 different species of ancient single-celled plankton.
Okay, so 4 miles down, enduring intense heat and pressure for 2 billion years. How did scientists verify that these were truly indigenous, deep fossils and not, contamination introduced by the drilling mud from the surface?
That's the critical methodology challenge, and they were very aware of it. They employed rigorous techniques, including specific chemical markers and isotopic analysis. They looked for unique carbon and nitrogen signatures that indicate chemosynthesis.
Chemosynthesis.
Life surviving by metabolizing minerals and chemicals in the rock rather than photosynthesis from sunlight. The presence of this preserved carbonaceous material under conditions that should have completely destroyed it was conclusive. It was native to that depth.
The fact that these organisms, or at least their remains, survived and flourished in a zone without sunlight, relying only on chemical energy, that's profound.
It is. It dramatically pushes back the timeline for life in the deep subsurface. It helped establish the concept of the deep biosphere as a viable, expansive habitat.
And some scientists now estimate that the total biomass of microbial life in the deep subsurface, these extremophiles living off mineral metabolism, might actually rival or even exceed the total biomass of all surface life combined.
It's a staggering thought, a hidden world of life beneath our feet.
And this ties directly back to space exploration, doesn't it? If life could survive these utterly alien subterranean conditions right here on Earth, in the absence of light, under crushing pressure, what does that imply for the search for life beyond our planet?
That is the essential astrobiological connection. Kola provided a perfect terrestrial analog. If microbial life can survive kilometers beneath the surface here, where the surface is lush and temperate,
it raises the strong possibility that life could exist beneath the hostile surfaces of other celestial bodies.
Exactly. Think of potential ecosystems beneath the frozen crust of Jupiter's moon Europa, where we know liquid water exists, or deep within the basalt layers of Mars. Kola showed us that life's potential habitat is far, far wider than we ever imagined.
So beyond the life in the water, the project was ultimately halted by the physical environment itself, which was far more extreme than any other models predicted. Let's talk about the thermal gradient.
The temperature gradient was the primary project killer. Initial geological models, based on generalized heat flow for the region, suggested that the temperature at 12 kilometers would be around 100 degrees Celsius.
Which is hot, but manageable with 1980s technology.
Manageable, yes. The reality, however, was 180 degrees Celsius. That's 356 degrees Fahrenheit. A massive, massive discrepancy.
Nearly double the predicted temperature. What caused that extreme localized heat flow?
Well, it suggests one of two things. Either there was localized, highly concentrated radioactive decay happening within those deep granitic layers, or a change in the physical properties of the rock itself was trapping heat, preventing it from dissipating upward efficiently.
Either way, 180 degrees Celsius is pushing the absolute limits of standard materials.
It is. It causes drill bits to soften, electronic sensors to fail rapidly, and the drilling fluids to break down.
And the unexpected gas pockets just compounded the issues, didn't they?
They absolutely did. As they drilled into the deeper sections, the team encountered significant pockets of hydrogen gas being released from the rock. Hydrogen. The drilling mud that pressurized fluid used to cool the bit and carry debris up began to bubble violently. The crew on the surface said it looked like it was boiling.
That sounds incredibly dangerous. It would alter the mud's density and viscosity, throwing off the whole pressure balance.
It was a huge technical headache. The hydrogen was likely a byproduct of that same metamorphic expulsion we discussed, ancient water reacting with iron-rich minerals under extreme pressure and heat, liberating H2 gas.
So the rock was bleeding gas too.
This rapid, unpredictable gas release threatened the stability of the borehole and required constant, precise adjustments to the mud's pressure and weight, making that final push agonizingly, painstakingly slow.
Before we delve into the fundamental physics that permanently defeated the Kola project, we have to pause for a moment to address the spectacular urban legend that surrounded this endeavor.
Ah, yes.
A story that shows just how deeply mysterious and, frankly, terrifying we find the idea of probing the deep earth.
The infamous well-to-hell hoax. This legend gained enormous international traction around 1989, right at the time when the Soviet team was hitting their technical maximum and starting to scale back operations.
The story circulated widely, especially in certain tabloids and on religious broadcasts in the West, and it claimed that Soviet scientists had drilled a hole. Not in the Kola Peninsula, of course, but in Siberia.
The details always get mangled.
Right. And they'd broken through into a massive underground cavity.
And that when they lowered specially designed heat-resistant microphones down the hole, they recorded not geological processes,
but the chilling, undeniable audio of millions of tortured souls screaming in agony.
The claim was stark, it was simple. The Soviets had accidentally drilled a hole straight into the biblical hell.
It's an incredible narrative. It weaves together technological ambition, Cold War paranoia, ancient mythology. It's the perfect story.
But the reality, as is so often the case, is far more mundane.
Indeed. The entire story was eventually traced back to a specific, identifiable source.
A Finnish evangelical newsletter. They had published the account, but as a piece of religious-themed fiction and allegory. It was never meant to be taken as fact.
But it was picked up by American and European outlets that reported it as fact, and it just spread like wildfire.
It was amplified by the pervasive mystery surrounding any Soviet activities at the time. That secrecy created a perfect vacuum for sensationalism to fill.
They're trying to keep their technical challenges quiet, and the world just replaced that silence with screaming demons.
Precisely. And the accompanying audio recordings that circulated online and on tapes.
Easily debunked.
Very easily. Analysis showed they were almost certainly manipulated sound effects or clips from horror movies, perhaps layered with some eerie wind effects, repurposed to fit this spectacular narrative.
And on a purely physical and engineering level, the actual facts of the Kola borehole just completely negate the possibility of this scenario.
Absolutely. First, the borehole is extremely narrow, only about 9 inches or 23 centimeters in diameter at the bottom. There is no massive cavity for screaming souls to inhabit.
It's a pipe, not a cavern.
And second, as we just discussed, the temperature at the bottom reached 180 degrees Celsius. Any microphone or electronic device lowered to that depth would rapidly melt, fail, or be crushed by the pressure. You simply cannot sustain operations capable of recording sound in that environment.
So what the hoax really reveals is less about the state of Soviet technology and more about human psychology.
I think so.
We have this deep cultural, often spiritual boundary that we perceive between the surface world and the world below. And probing that boundary triggers these primal fears about the forbidden, the demonic, or just the great unknown.
It highlights that underlying anxiety that comes with scientific overreach. For all the rational, measured scientific intent behind the Kola project, the very act of journeying 7.5 miles down taps into ancient human mythologies about the underworld.
The physical reality, not the mythological one, is what finally halted the project. Kola stopped drilling in 1989, and despite all the technological leaps we've seen since then,
Advanced metallurgy, new sensor technology, massive computational power.
no one has managed to break that 12,262-meter record. It stands as this powerful testament to the fundamental physics of drilling deep.
It is a profound lesson in diminishing returns. The same 3 physical factors that defeated the Soviets in the late 80s still conspire to limit deep drilling attempts globally today.
And those are temperature, pressure, and rock mechanics.
Exactly.
So let's start by detailing that thermal barrier again, because 180 degrees C was only part of the problem. It's what that heat did to the equipment.
Correct. The geothermal gradient, the rate at which temperature increases with depth, was simply too steep. Sustained operation near or above 200 degrees C fundamentally changes the physical properties of your drilling equipment.
The most immediate failure point would be the drill bit itself, I assume.
It is. Drill bits rely on inserts made of things like tungsten carbide for their hardness, and those materials lose their necessary hardness and wear resistance rapidly as temperatures approach and exceed 200 degrees C.
So the bit goes from cutting granite to trying to cut granite with a piece of metal that's becoming soft and dull.
Exactly. The rate of wear becomes completely uneconomical, and your drilling efficiency drops to zero. But it's not just the bit.
What else fails?
All the specialized components for downhole steering and measurement, they rely on polymers and sensitive electronics, and those rapidly cease to function when the geothermal maximum is reached. Elastomers and seals fail, and the electronics just overheat and die.
So this means that breaking the Kola record isn't just about drilling a bit deeper. It requires a complete breakthrough in high-temperature materials, science, and downhole sensor design that can sustain, 250 degrees C or higher for long periods?
It's a materials science problem at its core. But even if we solve the heat problem tomorrow, we run directly into the second massive barrier, the crushing weight of the planet.
The lithostatic pressure, the weight of that 7.5-mile rock column pressing down on the borehole.
At the final depth, that pressure was roughly 3,000 atmospheres.
Which is 3,000 times the air pressure you feel right now at sea level.
Yes. And this pressure is constantly trying to squeeze the borehole shut. It causes the rock wall to fracture, to collapse, or to deform inward.
So how do you counteract that immense weight just to keep the hole from closing in on itself?
This is where the drilling mud system is absolutely critical. You have to circulate an extremely heavy, high-density drilling mud, often loaded with materials like barite, which exerts an outward hydrostatic pressure against the rock wall.
So you're fighting pressure with pressure.
It's a perpetual, delicate balancing act. If your mud pressure is too low, the formation pressure overwhelms it, the hole collapses, and you lose everything. The drill string is trapped forever.
But the reverse is also a risk, isn't it?
Yes.
If your mud pressure is too high, you can actually fracture the rock and lose the mud entirely into the formation.
That's the danger. It's called lost circulation. If the mud pressure exceeds the fracture gradient of the surrounding rock, your expensive, carefully engineered drilling fluid just escapes into the cracks. You lose circulation, and you lose your ability to control the borehole.
And maintaining that delicate equilibrium over 12 kilometers with constant fluctuations in pressure and temperature must be one of the most difficult engineering challenges imaginable.
It is perhaps the most difficult challenge in deep drilling.
And those first two factors, extreme heat and crushing pressure, they lead directly to the third and ultimately fatal issue for the Kola project, the changing mechanics of the rock itself.
This is the critical concept of plasticity or ductility. At surface levels, rock is brittle. When you stress it, it fractures and breaks cleanly, which is exactly what a drill bit is designed to do.
It chips away at it.
Right. But deep down, under that combination of 180 degrees C and 3,000 atmospheres of pressure, the rock behavior changes fundamentally.
It stops being brittle and starts behaving like extremely viscous plastic.
Imagine stiff taffy or hot glass. When stress is applied, instead of fracturing, the rock slowly flows and deforms. As the drilling commences and the pressure is slightly released by the action of the bit, the surrounding rock begins to flow into the borehole.
So the borehole wall literally closes up around the drill pipe, making any further advance impossible.
It creates enormous friction. The rock flows around and grips the drill bit, causing it to seize, to twist, or to get permanently stuck. Furthermore, the immense shearing action required to pull a core sample from this plastic rock often resulted in the sample deforming or extruding itself from the core barrel as the pressure was released.
They were defeated by the flowable nature of the deep crust.
Ultimately, yes.
And finally, we can't ignore the most mundane reason for the project's cessation, cost, and geopolitical change.
Absolutely. Deep scientific drilling requires sustained, immense governmental funding. The Kola project took decades and cost millions of rubles. Some estimates put the contemporary value easily in the hundreds of millions of dollars.
And then the Soviet Union collapsed in 1991.
And that sustained, centralized funding dried up immediately. While commercial drilling for oil has profit built in, pure scientific exploration requires national dedication. And that commitment simply evaporated in the early 90s.
So the Kola Superdeep Borehole holds the continental depth record. But it wasn't an isolated effort. The global context shows that this pursuit of the deep crust was a collective scientific ambition.
It was a true scientific race, in a way. Before Kola eventually surpassed it, the previous deepest hole was actually drilled in the United States.
The Bertha Rogers hole in Oklahoma.
That's the one. And Bertha Rogers was stopped in 1974 not by plastic rock or extreme heat, but by a very volatile geological feature.
What happened there?
It reached a very respectable 9,583 meters, so just shy of Kola's initial record. But the drilling was halted dramatically and definitively when the bit struck a pocket of molten, or at least near molten, sulfur.
Molten sulfur.
The incident effectively ended the project due to the extreme danger and volatility of the geology they'd encountered.
So the U.S. and the Soviets were kind of trading drilling records throughout the 70s. What happened after Kola demonstrated the physical limits of the technology?
Germany picked up the mantle of continental drilling with the KTB borehole. That's the German Continental Deep Drilling Program. It was drilled in Bavaria between 1990 and 1994.
And they reached about 9,101 meters.
Yes, but KTB was crucial because it wasn't just chasing a depth record. It was actively dedicated to testing the very same seismic models that Kola had just challenged.
So KTB went in with more advanced sensor technologies, specifically to confirm Kola's radical findings about that missing Conrad discontinuity.
Precisely. The KTB project confirmed Kola's observation. It showed that the seismic reflections geologists had long relied on were often caused by high-pressure, fluid-filled fractures deep within the crust, and not necessarily by major shifts in rock composition.
So it provided a massive validation for Kola's ground truth lesson.
A huge validation from a different part of the world, which is critical in science.
And then we have the ocean drilling projects, which have a different strategic goal entirely. They leverage the fact that oceanic crust is much thinner.
That's the Integrated Ocean Drilling Program, or IODP, a vast international effort. Their strategy is fundamentally different from Kola's. While continental crust can be 30 to 70 kilometers thick.
Oceanic crust is only 5 to 7 kilometers thick.
Right. So they sacrifice the absolute vertical depth record in exchange for reaching a deeper, more profound boundary layer.
A moho.
Exactly. The ultimate long-term scientific goal of the IODP is to physically sample the Earth's mantle by penetrating the Mohorovičić discontinuity. The moho, that critical boundary separating the crust from the underlying mantle.
And they haven't done that yet, have they?
Not yet successfully. But drilling into oceanic crust is the most realistic path to retrieve rock samples from the mantle itself, which is something Kola, drilling through the thick continental crust, could never have hoped to achieve.
So Kola remains the king of the continental scratch, while the IODP continues the quest for the ultimate prize, a piece of the mantle.
A good way to put it.
So what does this all mean? We've covered the decades-long engineering battle, the catastrophic failures, that bizarre sound from hell hoax, and the profound physical limits that stopped the drill bit. Beyond the records and the heat, what is the lasting global legacy of the Kola Superdeep Borehole for Earth science?
Well, I think the legacy is defined by 4 core lessons that fundamentally revise geology, biology, and even material science.
And the first, and most enduring, seems to be that direct observation, the ground truth of the core samples, must always hold primacy over indirect models.
It has to. The missing Conrad discontinuity is the perfect canonical example of that scientific humility.
So one hole in the ground basically forced geologists to rewrite their textbooks.
It did. Kola forced geologists worldwide to acknowledge that their seismic and gravity models, while highly useful, could be fundamentally flawed because they were misinterpreting physical conditions like fluid-filled fractures as compositional boundaries. It spurred a complete reevaluation of how seismic reflection data is interpreted across the globe.
The second key legacy is that vast expansion of the deep biosphere concept, which Kola really helped champion.
The discovery of those 24 species of ancient plankton fossils cemented the deep biosphere as a recognized, massive, and ecologically significant habitat. We now know that microbial life can survive kilometers below the surface, completely independent of solar energy, by metabolizing the minerals and chemicals around them.
It redefined the thermodynamic boundaries of where life can exist, both here and potentially elsewhere in the cosmos.
It did. It forced us to recognize that life can be deeply integrated into the planet's geochemical cycle, surviving environments that we previously thought were completely sterilized by heat and pressure.
The third legacy relates back to the discovery of that unexpected ancient water. This water wasn't just a curiosity, it was a catalyst for fundamental geological processes.
That's absolutely correct. Kola highlighted the crucial dynamic role of deep water. The hydrological cycle extends far deeper than we ever imagined, and this water is critical to planetary processes. It acts as a solvent and a transport mechanism, influencing rock metamorphism, how rock changes under intense heat and mineral formation.
And critically, that deep water impacts tectonic activity and hazards, doesn't it? Like earthquakes.
Yes. The presence of highly pressurized water within faults and fractures can significantly reduce the effective stress on those faults. It essentially acts as a high-pressure lubricant.
Making it easier for them to slip.
Exactly. This directly influences where and how energy builds up, impacting the mechanism and frequency of earthquake generation. Furthermore, water drastically lowers the melting point of rock, which influences volcanic activity, particularly in subduction zones. Understanding the deep water regime is now considered essential for hazard prediction.
And finally, there's the often overlooked international scientific value of the project.
Right. While it was driven by Cold War competition, the ultimate result of the Kola project was a global sharing of data and core samples. The breakthroughs in understanding crustal structure, rock mechanics, and deep biology benefited the entire global geological community.
So it stands as a powerful example of how pure scientific ambition, regardless of its funding source, can transcend political boundaries and accelerate our understanding of the planet.
It really does.
Today, the Kola Superdeep Borehole site is, well, it's a monument to ambition and entropy.
It is. After funding dried up following the collapse of the Soviet Union, the project was officially closed in 1992, and the site fell rapidly into dereliction.
The photos from the site are quite haunting.
They are. The main drilling rig has been dismantled for scrap, the laboratories and housing facilities are just rusted-out ruins, and the whole complex is slowly being reclaimed by the Arctic tundra.
And the single tiny opening to the deepest hole on Earth is just sealed with a massive welded metal cap. It marks the end of a physical era of exploration.
A very literal dead end.
But the record remains, and the question remains, can we ever go deeper?
To break 12,262 meters, we would need radical disruptive technology to overcome those three primary physical barriers: the heat, the pressure, and the plastic flow of rock.
What would that look like?
Researchers are exploring experimental methods like thermal drilling, which uses extreme heat from a laser or plasma to melt or even vaporize the rock instead of relying on mechanical grinding.
So you melt your way down instead of drilling?
In theory, yes. But these technologies are currently experimental and incredibly expensive to scale up for sustained industrial use. So we need an economic incentive to push past the Kola limit.
And that is the most realistic path forward, isn't it? The primary commercial driver right now is super hot rock, geothermal energy.
That's the big one. Extracting clean, renewable energy from the extreme depths of 10 to 20 kilometers requires solving the exact same materials and physics hurdles that stopped Kola.
So if that clean energy becomes economically viable, that commercial investment will undoubtedly drive the technological breakthrough needed to finally break the depth record.
It's the most likely way it'll happen.
The Kola Superdeep Borehole remains this profound moment of scientific realization. Despite throwing decades of resources and ingenuity at the problem, the Soviets only reached 12,262 meters.
And we need to remind ourselves of the context one final time. The Earth's radius is roughly 6,371 kilometers.
So that deepest hole only penetrated about 0.2% of the way to the center.
It's barely a pinprick on a planetary scale. We are masters of the surface and explorers of the cosmos, yet Kola is the ultimate reminder of our humility regarding our own home.
We know more about the atmospheres of distant planets than we know about the deeper layers of the lithosphere right beneath our own feet.
Absolutely. The most compelling frontiers aren't always out in space. Beneath that welded metal cap in the Russian tundra lies a realm of ancient, pressurized water, of rock that flows like stiff plastic, and of hidden life that operates entirely outside our familiar ecosystem.
The Kola Borehole is a sealed passage to a world that remains largely unexplored, alien, and utterly mysterious.
It stands as a silent challenge, a testament to how much we still have left to discover right here, underfoot.